Good morning. We are at the SciTime studio. With me today we have Guy Walker from University of Buckinghamshire, UK, to talk about computer gaming.
Hello, yes. I'm the course leader for two games courses at Buckinghamshire University, as well as monitoring the course that we run here at SciTime. Okay. I'm over here on my annual visit, okay, and come to have a chat with you about programming in the games field.
So Guy, let's talk about some of the things that they learn here undergraduate level, and then some of the theories that they learn here, and also how they apply that in the real world game design and game programming.
Yeah. Okay. Well, our students come in with a diverse set of backgrounds, so they don't necessarily have done any programming before. So we teach them the principles of programming in the first year, and then in the second year we try to specialise in different areas. So we'll be looking at graphical programming. So this is the low-level code, okay, where they can create simple geometric objects, applies textures to them, learn about light theory, okay, learn about 3D positioning. They then go on to look at shader programming. So shaders are small C-based programs that will run on the GPU, that's the graphics card, and the shader's sole purpose is to work out the color of each of the pixels in the screen. Okay. So that's very low-level programming, and then they come up to a sort of higher-level programming, so subjects like AI, artificial intelligence. Here they'll be trying to create characters whose behavior mimics almost like human-like behavior. Okay. So sort of very low principles, we'll be looking at senses, how they can determine perhaps if the player is in front of them. Okay. Right. So again, mathematical principles like dot product being used there, some trigonometry.
Physics as well, I suppose.
Physics as well, yeah. Right. Also things like decision making. This is where it starts to become a little more complicated, things that perhaps we're looking in the third year. Right. So there's various different techniques they could use. One of the most popular and versatile ones is goal-oriented action planning. Right. Here, what we do is we think about all the different things that a non-player character could do, okay, and specify them as tasks, almost like objects within our code. Okay. Right. So you could perhaps sit down, you could drink, you could open a door, you could fire a gun. So we could have hundreds of these tasks, and each of these tasks would have what we call the preconditions, things that they must have or have done before they can enter that task. Okay. So before we can fire a gun, we must have a gun. Okay. So we must have collected it, which is another task. Okay, and then we have actions, things that have been done. Okay, once the task is complete. Okay, so firing a gun, perhaps one of the effects of that would be we'd have one less bullet. Okay. And we've set up all these tasks, and then we use an algorithm to search through the tasks. Okay, rather like a pathfinding algorithm. Okay. So we specify a goal, which could be kill the player. Right. Okay, and based on its current understanding of what it's got. Okay, it may say, I've got a task to fire a gun, which requires a gun. Okay, do I have a gun? No. Do I know where it is? He may say, well, no, I don't know where the gun is. So it'll throw that task out. Okay. However, he may say, one other way I could kill the player is to drown him. Okay, so how do I drown him? Well, I know where the sink is. Okay, so what I could do, have I got the knowledge of how to turn the water on in the sink? Yes. Okay, so that'll be my task. So I'll work my way to the bathroom. Okay, grab the player, put his head in the sink and turn the sink on and kill him that way. So it's a very flexible way. Okay, and it produces it's very difficult to predict which of the tasks he's going to execute. So it gives you that flexibility and non-repetitive behavior.
Also, you said that these tasks, they are independent of each other and they need to be executed in parallel, perhaps?
They're executed, there will be a sequence in which they're executed, but the beauty is we can just add tasks quite independently, as and when we see fit.
Now, usually, when our children, when they learn programming, it's usually a sequential sort of programming. Now, here, I suppose we look at parallel programming as well.
Well, yeah, that's an interesting point. Yeah, because because the AI is getting more and more complex. Okay, the code is getting more verbose. Okay, there is a need to really take that code and execute it somewhere other than the CPU, because the CPU is being bogged down with other tasks, and you don't want that bottleneck. So one solution might be to parallelize this code. Okay. That's only appropriate in certain situations, where it is appropriate to do so. Okay. Usually, the parallelism is used within the shaders, because you can imagine there's so many pixels that need to be populated in parallel. So that's an ideal example. But there are instances where you can parallelize the AI code, and one of these may be within flocking behavior. Because you'll come across a flock of birds. They all tend to sort of move in generally the same direction. And the flock algorithm works on sort of three principles. One of them is that you take the average of all the bird's directions, and you make your bird move in that direction. You look at all its neighbours, and you maintain a distance between the neighbours so you don't keep bumping into them. So there's all these calculations got to be done, but they can be done in parallel, because what we could do is say each of these birds, has got these algorithms to work out. Let's do that in parallel. So now, rather than doing this on your CPU, which has probably got 4 cores, or if you're very rich, 6 cores perhaps, we could do this on a GPU, because the GPU cards have got up to about 3,000 cores. So that's a lot of processing we can do. Now what we don't want to do is have to do all this manually. I don't want a lot of machine code, so things are going to get very complicated. So what we do is we use an NVIDIA framework called CUDA. And that sits on top of the hardware and allows us through our programs to access the cores of the GPU.
The CUDA is from the NVIDIA.
Yes, an NVIDIA technology.
So it runs on the NVIDIA.
It runs
hardware.
on NVIDIA. You'll find that over the last 4 or 5 years, most graphics cards produced by NVIDIA are CUDA enabled. And that's great because when you come to not necessarily games programming, but when you're processing a lot of data, maybe millions, if not trillions of bits of data that you need to do in parallel, we can set it up on CUDA very efficiently, so we can say, this particular function needs to be executed against all these bits of data, and we can specify how many process in parallel, and each processor can have multiple threads as well, so we can specify how many threads. It's a bit more involved in that, but that's generally what it's like. Any idea, any lesson that we can give it to our students as to who are looking at the games programming as a career? Where should they start, and what are some of the prospects they have? Well, the games industry is relatively small compared to the IT industry as a whole, so it's quite competitive to get a job within it. But one thing that the industry are looking at now is portfolios. Typically that was the artist who was meant to develop a portfolio, but now coders as well. So you can imagine a games company will advertise a job and they get thousands of applications through, and there's a sifting process. And one of the things that they'll be doing is looking at your portfolio. So if you have an online presence, with examples, not only your code, but how the code works, perhaps video shots, screenshots of how the code works, the mechanics works, that'll certainly help you get foot in the door.
Are there any particular places where they look for, like for example, graphic design? People use Behance from Adobe. Similar places for gamers or game designers, programmers?
Well, the games artists, I mean, they would expect to use 3D Max, Maya for the animation. So Max typically for modeling, Maya for animation, although the two packages are sort of slowly merging. In terms of the code, C++ is the de facto language for the games industry, because of the performance. So they tend to avoid the .NET environments. Mobiles, slightly different, maybe Java, but for your AAA titles, they'll be all running on engines written in C++.
That's very right. Thank you very much for that very in-depth information about the gaming industry, and we'll see you soon.